In the previous video, we discussed Kruskal's algorithm, which uses a greedy approach to find a minimum cost spanning tree of an undirected connected graph. Here, we'll discuss another greedy algorithm called Prim's algorithm, which finds an MCST of a graph. Billy will first explain to you Prim's algorithm, and I will discuss its C++ implementation.
In Kruskal's algorithm, we start with a group of components, each consisting of a single vertex, and repeatedly merge two components connected by a minimum weight edge until we get a single component, which is our final MCST. In Prim's algorithm, on the other hand, we start from a single tree consisting of only an arbitrary vertex of the given graph and growing the tree naturally. At each stage, we add a new edge to the tree already constructed until the tree contains all the vertices of the graph. Suppose we are given an undirected graph G with a set of vertices V and a set of edges E. Let N be a subset of vertices, and T a subset of edges, which can be regarded as a tree. Initially, N contains a single arbitrary vertex of the graph and T is empty. At each step, Prim's algorithm searches for the shortest edge, U, V, such that U is in N and V is in V minus N. It then adds V to N in the edge U, V to T. Consequently, at any instant, D forms an MCST for the vertices in N. We continue thus until all vertices of the graph have been included in N. To elaborate on the algorithm, let's consider again this graph, which we have used in the video of Kruskal's algorithm. In the beginning, N has only one arbitrary vertex, which is A. Its complement, V minus N, has the remaining vertices, B, C, D, E, F, and G. There are two edges connecting these two components. They are A, B with weight, 7, and A, D, with weight, 5. The algorithm chooses the least cost edge, which is A, D, with weight, 5. It includes D in set N, so now set N has vertices A and D. Set V minus N has vertices B, C, E, F, G. Now the edges connecting these two components, N and V minus N are AB, with weight, 7 dB, with weight, 9 DE, with weight, 15 and DF, with weight, 6. The algorithm chooses the least cost edge D, F, with weight 6 and includes F in set N. So, now N has vertices A, D, F, and V minus N has vertices B, C, E, G. In a similar way, it next chooses the edge A, B, with weight 7, and includes B and N. Now N has A, B, D, F, and V minus N has C, E, G. Next, it chooses the edge B, E with weight 7, and includes E and N. Now N has A, B, D, E, F, and V minus N has C, G. Next, it chooses the edge E, C, with weight 5, and includes C and N. Now N has A, B, C, D, E, F, and V minus N has G. Next, it chooses the edge E, G, with weight 9, and includes G and N. Now N has A, B, C, D, E, F, G, and V minus N is empty. So the algorithm stops and the tree T contains the chosen edges AD, DF, AB, BE, EC, and EG. Here's the pseudocode for the algorithm. We are given a graph G with a set of vertices V and a set of edges E. We declare a set T to be empty and a set N. We include an arbitrary vertice from V and N. While N is not equal to V, that is, V minus N, is not empty, we do the following. We find an edge, say E, equal to U, V of minimum weight such that U is in the set N and V is in the set V minus N. We then include the edge E in T and include the vertex V in N. When we exit the while loop, T contains a minimum cost spanning tree. We can prove that Prim's algorithm finds a minimum cost spanning tree. The proof is by mathematical induction. Here's our hypothesis. Prim's algorithm gives a minimum cost tree T for the subgraph Gn, E' at each step, where E' is the set of edges connecting all the vertices in N. Let's call this hypothesis H. Proof by induction. Let N equal the number of vertices in N. 1. Base cases, N equals 1, 2, H is obviously true. 2. Assume that H is true for the subgraph GK with N equals K vertices. 3. Consider the next step, when N equals K plus 1, which adds a minimum weight edge. Connecting N to the outside, complement, of N, so the tree TK plus 1, which includes the newly added edge of the subgraph GK plus 1, is still a tree. Since it has added a minimum weight to TK which has the minimum cost, the total cost of TK plus 1 is also minimum. So, H is also true for N equals K plus 1. When the algorithm terminates, N equals V, and the tree D obtained is an MCSD of GV, E. This figure shows that a shortest edge is added to TK, to form TK plus 1. Note that the number of edges in T is always equal to the number of vertices minus 1, as we start with 1 vertex and 0 edges, and each time when we add a vertex, we add an edge. If N is the number of vertices in the given graph, the main loop of the algorithm is executed N minus 1 times. At each iteration, the find operation takes a time theta n, as you will see in its implementation. Kruskal's algorithm takes time theta m times log n, where m is the number of edges of the graph. For a dense graph, one that has many edges, m is about n square. Kruskal's algorithm takes time theta n squared times log n, so Prim's algorithm is better. On the other hand, for a sparse graph, m is about n. Kruskal's algorithm takes time theta n log n, and is better. There exist other algorithms more efficient than either Prim's or Kruskal's.
Now, this is the C++ implementation of Prim's algorithm. Okay. So in the program, we have to include these headers. Okay. We define NV to be the number of vertices, and in our example it is 7. So we use the graph we just discussed as an example. And here we use an adjacency matrix to represent the graph, okay? So which is simpler. So if there's no edge connecting the two vertices, then the edge weight is infinity. We say 8 to 999. Okay, and for this graph, so A is 0, 1, okay, this AB, okay, is 7, okay, and A is 0, 3, that's AD, okay, that's 5, and A 1, 2, there's a BC, okay, that's 8, and so on. Okay, so we assign these values to the two-dimensional array, which is the adjacency matrix. Because it is an undirected graph, so the matrix is symmetric. So we make the Aij to be Aji. So we just do these ones, and then use these for loops to assign the other half. So we can print out the matrix, okay, or retro adjacency matrix of the graph print this out like this. Okay. So we define the array V to represent the vertices A, B, C, D, E, F, G. So that means when it's 0, we print it out as A. When it's 1, we print it out as B, and so on. Okay. So we print out the vertices, okay, vertices name, and then the weight. Okay. And if it is infinity, we print out the entry as X. Okay. Others we print out the values. Okay. Now let's copy and compile this and see the matrix. And copy this. Okay. So this direction is empty. And paste this. And let's just print out the matrix first. Okay, without printing out the tree. Okay. So we just print out this matrix. So we compile this. So Prim. So we generate the executable. So now we execute it. Okay. So you can see that this is the adjacency matrix, okay, for the vertices A, B, C, D, E, F, G. So from A to A, we make it infinity. A to B, there's 7. Okay. And B to A is also 7. A to D is 5. Okay. A to C is infinity. Okay. B to C is 8. Okay. C to B is also 8, and so on. Okay. So that's the matrix which is given. Okay. And to implement Prim's algorithm, we define an add class. We did that. We discussed this in the Pseudocode algorithm video. Okay. Now this is the class add. We have the data member start word, means the starting vertex, and word ending vertex. Okay. The add goes from the start word to end word, and then the weight. We have a set function to set as to start vertex, E to end word, W to weight. Okay, so straightforward. Okay. And so this is the smaller than operator. We define this so that we can use the insert function of the standard template library in C++, okay, of the set class, okay, to insert an object, an add object into a set. Okay. So we just compare the weight. Okay, if the weights are equal, we compare the vertices. Actually, I think this could be the start word. Okay, it's better. So there's a minor mistake here. So this is the edge, and we can print out the edges of a tree. So this is the function print edges. So we are given a set of edges. Okay, we can print them out in the form of adjacency lists. Okay. So we define the vertices as A, B, C, D, E, F, G. Okay. And then we declare NV edge lists. Okay, these are adjacency lists. Okay. A list for each vertex. Okay. And then an iterator IT to traverse, okay, is edge set. So from the beginning to the end, we traverse this tree T. Okay, and then we put the edges into the appropriate list. Okay, so we get this edge. Okay, and start vertex. Okay, as an edge list. As an adjacent list, we put that edge into that list. Yeah. And then after that, we traverse each adjacency list, okay, each edge list, okay, and from begin to end, okay, and then print out the starting vertex, okay, that's S, okay, and ending the vertex, the C, and the weight. Okay. So that's how we print the edges of a tree T. Okay. And now this is the implementation of the Prim's algorithm. This is a straightforward implementation, but not very efficient. So basically, a straightforward implementation of this. Okay, we define E of minimum weight such that U is in N, V is in V minus N, and put them in T and N. Okay. So we declare the empty set T, okay, and a vector N to represent the vertices of N. Okay, so we start with 0. We start with an arbitrary vertex, and here we start with vertex 0. Okay, and then we repeat this n minus 1 times, nv minus 1 times. Okay, if the n is not the set of vertices, not the full set of vertices, okay, then we do this. So we set the minimum weight to infinity, 999. And we declare two variables, mu, mv, basically they mean minimum u, minimum v, the vertices of the minimum cost edge we found. Okay, so we examine each vertex in the set n. Okay, and find out its shortest edge. Okay. So U is Ni, okay, and we consider all the vertices, and in V minus U, sorry, in V minus N, okay, V minus N. Okay. But here we consider all vertices, but if it is in N, then we continue. So we use this phi function. If say V is also in N, then we skip. Okay, we only consider V minus N. Okay, only consider this this set. Okay, V minus N. Okay, vertex in V minus N. And if V is in V minus N, and if its weight, okay, the weight of the edge is smaller than the minimum weight found so far, then we update the minimum weight, okay, to the weight of the edge, and then the minimum U is that U, minimum V is that V. So we examine all the vertices in V minus N, okay, and eventually we get the minimum weight edge. Okay, so we declare this edge and set the edge to mu mv with that weight, okay, and then put that in T, okay, and put mv in N. Okay, so this is very straightforward. Now, the implementation here consists of this loop and this loop, the double loop. Okay, So it is straightforward but not very efficient. Okay, but it works. Okay, now let's try this. So we compile this. So this is called Prim. Okay, this function. So we compile this again. Now we uncomment this. This is Prim. So we provide the adjacency matrix A, okay, and then it returns T, the tree, okay, and then we print out the edges of it. Okay. So we compile this again, okay, and then execute this again. Okay. So we get this MCST, and it is printed out as adjacency list. Okay, the AB 785. Okay. So that's what we want. Okay. So as you can see, so we have this edge AB is chosen, and then AD with weight 5. Okay. And then for B, BE is 7. Okay. And then DF, that's 6, okay, DF 6, and EC 5, ET 9, okay. Now this is an undirected graph, so it is understood that when it has AB, BA also exists, okay, it is not printed out twice, okay, so it is printed out once. So if you want, you can print out BA here, and then say CE here, but I think this is clear enough. Okay. So this is very straightforward, but not very efficient. Now we discuss another implementation which is more efficient. Okay. So again, we provide the adjacency list A, and we have NV entries, okay, and it returns the tree T. So again, to start, okay, we declare T as a set of edge, but it is empty at the beginning. We also declare two arrays with NV empties. NV is the number of vertices. Okay, one is called mean cost. The other array is called nearest. So nearest I is the vertex in N that's nearest to vertex I in V minus N. Okay, so you have the vertex I, a vertex in this set V minus N, okay, and then there's a vertex in N, okay, that's nearest to it, okay, and this is given by nearest I. Okay. Nearest means minimum weight, okay, minimum weight, or minimum cost. Okay, so mean cost is the cost from I to nearest I. Okay, the minimum cost edge. Okay, I nearest I. Okay. So at the beginning, there's only one vertex 0 in N. Okay. So we do that for all other vertices. Okay. So V minus N contains 1 to MV minus 1. Okay. So the nearest of all of them is 0. Okay. But because N is has only one vertex 0, and the mean cost is the A0 to I, or AI0. Okay. So that's what we have at the beginning. Okay, we declare this variable mu mv, minimum u, minimum v. So we repeat this nv minus 1 times, okay, to consider all the vertices, the remaining vertices, 1 to nv minus 1. So to start, we set minimum weight to be infinity 999 here, okay, and we check all the vertices, but if the vertex is in n, then we skip it, okay, because we just need to consider the vertex in v minus n. Okay. The trick here is that if the vertex is in n, we set its mean cost to be -1. So that means if mean cost v is smaller than 0, then v is in n, we skip it. Okay. And we start from 1 here, so we don't consider 0. Okay. So at the beginning, we consider all the vertices in v minus n. Okay. And if the mean cost of v is more than mean weight, okay, as a smaller weight, okay, then we set mean weight to mean cost v, okay, and update the mv, okay, to be v, and mu to be that vertex. Okay. So when we exit, okay, we find the mu and mv. So mu mv is the edge with minimum weight, okay, and mu is in n, okay, and mv is in v minus n. Okay. So again, we declare an edge, okay, and set the edge to be mu mv start vertex and vertex, and the weight given by a mu mv, and then put that into the set t, okay, and we also put mv, okay, now it is in n, okay, we expand our n, just like this diagram. When we include this one, we expand our t, okay, or an n, okay, including this new one. Okay. So we do this nv minus 1 times, okay, and then we get the t. Okay. Now here you can see that we don't have a double loop inside this for loop. Okay. So we only have a single for loop. Okay. And this also, this for loop is not inside this. Okay. So because of this, okay, the cost of this for loop is theta nv, okay, and the complexity of this algorithm is theta mv squared. Okay, so that's what Billy mentioned. Okay, here. Okay. So we can compile this using this algorithm, which is more efficient. So we call this Prim 1. Okay. So now let's compile this again. So we just need to change this to Prim 1. Okay. So we use the other algorithm. The other function, okay, and then execute that again. So you can see that we again get the same result. Okay, and basically the same result. Now you can compare that. Okay, so AB, AD, okay, BE, okay, and DF6 and EG9. Okay. So again, this is undirected graph. So it is understood that BA7 is also an edge, so we don't print it out twice. Okay. So you can try this yourself, and you could also improve upon it. Okay. So if you think that this video is useful to you, please click like. Okay. And thank you for watching. Okay, bye.